Hey, Class 10 students, welcome. Today we're going to crack the code on a chapter that is absolutely huge for your board exams. Yup, we're talking about Chapter 9 from your NCERT science textbook, Light, Reflection and Refraction. If you can nail this chapter, you're setting yourself up for some serious marks. So let's jump right in and get you totally exam ready. So here's our game plan. First, we'll cover the absolute basics of light. Then we'll decode the first big idea, reflection, and what happens in mirrors. After that, we'll tackle the second code, refraction, and how lenses work. And finally, we'll get to the master key, all the essential formulas you'll need to unlock every single problem on your exam. All right, let's kick things off. Before we get into all the fancy mirrors and lenses, we have to start with a question that seems almost too simple, but the answer is the foundation for this entire chapter. Now really, think about it for a second. You walk into a room, it's pitch black, you see absolutely nothing. You flip a switch, and bam, the entire world just appears. What's actually happening in that moment that makes everything visible? Well, the answer is kind of mind-blowing in its simplicity. We don't actually see objects. What we see is the light bouncing off of them. An object gets hit by light, it reflects that light, and when those reflected rays enter our eyes, our brain goes, aha, there's something there. That's it. That's the secret to how we see anything at all. Okay, so let's crack our first code. We know light bounces, but what happens when it bounces off a curved surface, like a spherical mirror? This, my friends, is where the real fun begins. You want to remember this forever? Go grab a shiny spoon. Seriously. The inner part, the bit that would hold soup, it caves inward. That's a concave mirror. It brings light rays together, it converges them. Now flip it over. The backside bulges outward. That's a convex mirror. It spreads light rays apart, it diverges them. Spoon? Best study tool ever. Okay, before we can draw any diagrams or solve any problems, we've got to learn the language. These 6 terms are the absolute bedrock. The pole, that's just the center of the mirror's surface. And the center of curvature, that's the center of the giant imaginary sphere that the mirror was sliced from. Knowing these points is non-negotiable. And this leads us to a beautifully simple but incredibly powerful rule you'll use constantly. R equals 2F. All this means is that the focus point, F, is always exactly halfway between the mirror's surface and its center of curvature. It's a tiny formula, but it's absolutely critical. Now, look closely at this slide. This is basically your cheat sheet for concave mirrors. This table, straight from your textbook, tells you exactly what kind of image you'll get based on where you put the object. If you memorize this, a whole bunch of exam questions just became free marks. So why does any of this matter? Well, you see it every day. The headlights on a car use a concave mirror to shoot out a strong, parallel beam of light. Dentists use them to get a magnified view of your teeth. And the rearview mirror on that same car, that's a convex mirror, giving the driver a really wide view so they can see everything behind them safely. All right, time to decode number 2. We've mastered what happens when light bounces. But what happens when light goes through something transparent, like a piece of glass, and bends? That, my friends, is refraction. And it's the science behind every single lens. And just like with mirrors, we have 2 main types. A convex lens is thicker in the middle. Think of a magnifying glass. It converges light to a single point. A concave lens is the opposite. It's thinner in the middle, and it spreads light out. It diverges it. And yep, you guessed it, here's another one of those super important exam tables. This one tells you everything you need to know about the image formed by a convex lens. If you can master this table and the mirror table, you'll be able to predict image characteristics like a pro. And now for some good news. Concave lenses are way simpler. The rule is incredibly easy to remember. It doesn't matter where you put the object. A concave lens will always give you an image that is virtual, upright, and smaller. Always. No exceptions. Okay, let's get to it. The final, and I'd say most critical section. We have the concepts down. Now it's time to grab the master key, the rules and formulas that will let you solve any numerical problem they could possibly throw at you in the exam. Listen up, because this is everything. Before you even think about using a formula, you have to master these sign conventions. Think of it like the grammar for the language of optics. If you get your plus and minus signs wrong, your entire answer will be wrong, period. You have to know these rules inside and out. And here it is, the beautiful, elegant mirror formula. This one little equation connects the object's distance, u, the image's distance, v, and the focal length, f. Now look very, very closely. See that sign in the middle? It's a plus sign. Do not forget that. Now let's look at the lens formula. It looks almost identical, right? But there is one tiny exam-destroying difference. That sign. For lenses, it's a minus sign. It's 1 over v minus 1 over u. This is the single most common mistake students make. Bird this difference into your brain. Magnification, M, is simple. It tells you how much bigger or smaller the image is. And the sign is a secret code. A negative M always means you've got a real inverted image. But check out the formulas. For mirrors, it's M equals negative V over U. For lenses, that negative sign just disappears. It's just V over U. And finally, let's talk about the power of a lens. It's really just the inverse of the focal length. But you have to make sure the focal length is in meters. The unit is the diopter. And the rule is simple. Convex lenses have a positive power, and concave lenses have a negative power. Easy to remember. This quote is just perfect because it explains what refractive index actually is. It's not just some random number. It's a speed limit for light. It tells you exactly how much a material slows light down. A diamond's refractive index of 2.42 literally means light travels 2.42 times slower in a diamond. Cool, right? All right, pop quiz time. Let's see if you are paying attention. A convex mirror has a radius of curvature r of 32 centimeters. So, what's its focal length f? Remember the rule, r equals 2f, so f is just half of r. The answer is 16 centimeters. See, you've got this. Okay, final challenge. A doctor's prescription says a lens has a power of plus 1.5 diopters. What does that little plus sign tell you? Well, positive power means it's a convex lens. And what do convex lenses do? They converge light. Exactly. You nailed it. So there you have it. We've cracked the code of light, at least by treating it as a simple, straight ray. But here's a final thought to leave you with. In reality, light also behaves like a wave, and that wave nature changes everything. But that's a much bigger puzzle, one for you to solve in your higher classes. For now, you have a rock-solid foundation to go out and absolutely ace this chapter. Good luck.